of by MS Excel. So today we are going to cover Horner's plot by application of pressure buildup test, and then we will get into frontal displacement, how we are going to measure the displacement of waterfront that we are going to see in MS Excel. And next to that, we are going to discuss about flow regimes, the type of flow regimes, and how we can able to identify these flow regimes through pressure derivative analysis. So without further delay, let us get into the topic. Yes. So this is pressure buildup test. Like first of all, basically I will give information. So initially well will be allowed to flow for some time. Then after that well will be shuttered in. So during shut-in period, pressure will start to get built up. When the flowing period is there, the flow rate will be observed to reduce. Like I will be just, so you can see the pressure, it has been reduced during production period. Then after that, you can observe that pressure will start to get raised up. So while raising up, we are going to measure the parameters by observing this. So delta T is the time during shut-in period. So you can observe the hike of pressure over here. And if you have the data of pressure as well as shut-in time, then you can able to see these graphs. Based on that, we can identify different parameters like reservoir parameters, skin, fault, interference, limits of the reservoir. So reservoir permeability, that will help fluid to flow from what direction to where, that will be identified. Skin factor is the damage around well, that also can be identified through this test. And wherever faults are there, interference is there, and limits, where the boundary limits are there, that also can be identified through this test. Today we are going to see pressure buildup with a case study. Like we're going to see in MS Excel how the data will be understood to get these parameters, like how we can able to identify these, the patterns of this data, how Excel will help you to understand that. With that, we can identify these parameters. So for an ideal graph, this is how the graph looks to be. This is the equation given by Horner to identify permeability and skin. So PW is equal to PI minus 162.6 Q naught mu B by KH log TP plus delta T by delta T. So PW is wellbore pressure. So it may start reducing from reservoir pressure to surface pressure. So the pressure will be changing in wellbore condition. So that is PW. So once the production have been completely ceased, the wellbore pressure will be at minimum level. Then once the well was shuttered, then pressure starts to build from that minimum level to reservoir pressure, equivalent to formation pressure. So that is the value or range of PW. When it comes to PI, that is initial or undersaturated reservoir pressure. So this is a constant parameter. So wherever we use this parameter, that will be having a similar value. So there won't be any change in PI. Minus 162.6 Q naught. Q naught represents surface flow rate of oil. So the units for that is stock tank barrel per day. If you are measuring with respect to day, it will be day. If it is for hour, stock tank barrel per hour. Then mu represents viscosity of oil, B represents formation volume factor for oil, and K is the one which we are supposed to measure, that is permeability, and H is thickness, log TP plus delta T by delta T. So TP represents production time. So well have produced for some time. Then after that, it was shuttered. So the production period have been constant. So in pressure buildup test, the measurement of TP will always be same. It will not change, but delta T will change. since we will start measuring the pressure during shut-in period, delta T starts from 0. So when delta T is equal to 0, TP will be ending at that particular point, and the pressure will be expected to be minimum at a delta T when it is 0. That means the pressure corresponding to PW, not PI. So PI always will be constant, but when it comes to PW at a delta T is equal to 0, that represents shut-in is about to start. It haven't been started. So delta T is equal to 0. Just before shut-in, the pressure is observed to be the minimum pressure inside reservoir. Wellbore pressure is observed to be minimum just before shut-in period. Once shut-in period starts, delta T will start to click from 0 to 0 0.01, 0 0.02, like that. It will go on. It depends on the time scale that you are preferring. It could be like minutes or hours or 30 seconds or like 30 hours or 30 days, I mean days, 1 day or 2 days. Look, it all depends on the time parameter of the interest of industry, like industry of, I mean like the project or firm, whatever they are having the scale, that is dependent on that. So PW is wellbore pressure, reservoir pressure, and this is the term that we are going to use it to estimate permeability and log TP plus delta T by delta T. So it is in the form of y is equal to mx plus c. So in coordinate geometry, m represents slope. So if you consider PW as y and x as log TP plus delta T by delta T, then the slope between y and x axis, that is PW and log TP plus delta T by T, will be equivalent to 162.6 Q naught V naught B by KH. So M is equal to 162.6 Q naught B naught mu naught by KH. This is nothing but this value. So here, why we are taking slope as this equation, the reason behind that is to estimate the value of permeability by using other parameters. Like if you have Q naught, mu, B, and H, then if you could able to find out the value of M, then we can estimate the parameter like permeability, like K. And when it comes to skin factor, and one more thing here, there is no minus symbol, but actually slope will be having minus, since here y is equal to mx, that is plus mx. M is equal to minus 162.6 Q naught mu B by H. In this case, in Horner's plot for pressure buildup test, M is equal to minus 162.6 Q naught B naught mu naught by KH. That is the only adjustment we are supposed to do over here. Then next to that, yes represents skin factor, that is equal to 1.151 into P at 1 hour. This is after shut-in period, the duration of time will be progressive. So we need to have the pressure at 1 hour, the 1 hour standard pressure where the skin factor ends over there. So this is API standards. They will be giving for skin factor as 1 hour time period. So if you have the value of pressure at 1 hour during shut-in period, that value should be kept over here, minus PWF, where delta T is equal to 0. Delta T is equal to 0 represents pressure before shut-in. So shut-in period haven't been started. So before shut-in, what is the pressure? That is PWF at a delta T is equal to 0 by M. How we have measured M from this, y is equal to mx plus c. The same M we are going to use it over here, minus log K by 5 mu Ct. K represents, since you have already estimated permeability through slope, that value will be kept over here, by porosity, viscosity, total compressibility, and wellbore radius. So 5 mu Ct Rw square plus 3.23. So if you have all this value, you can able to estimate skin factor and permeability. So this is how generally the log looks to be. It is a semi-log graph. So you can see on the x-axis, it is logarithmic scale is there, but on the y-axis, it is a linear scale. So we can able to understand x-axis is not linear, it is logarithmic. And the coordinates on x-axis will be TP plus delta T by delta T. So TP represents production time period plus delta T is shut-in time period by shut-in time period. So this is a straight line equation. Initially, you can observe there is a deviation because of skin factor, and mostly it will come close to 1 hour. So if you see on the time scale, shut-in time is on the top of the graph. So you can see 1 hour, 5 hours, 10 hours, 50, 100, 500 like that. So from 1 hour onwards, skin factor will start to reduce. This is an ideal graph. So the value at P at 1 hour will be considered for skin factor. But in this graph, it haven't touched on the trend line over here, but we can take this pressure as a reference value to estimate skin factor. Then after that, it will start to deviate down and it will follow the trend like a straight line trend will be observed over here. So it will be continued. The intersection of this straight line on the axis will be considered to be initial pressure, like undersaturated pressure. So this is how the graph will be looking. Initially, there will be a deviation. Then after that, we are supposed to continue on a steady trend. And if you want to estimate permeability, we need to estimate slope. Slope was given to be minus m here. And the slope is not corresponding to all the points, only the points which were intersecting on the straight line trend on this graph. So we have to consider the points which were intercepting on that particular straight line. That straight line represents the slope of this particular pressure buildup graph. It is not these deviated points. So we have to identify these deviated points and we need to ignore while measuring the slope for this particular graph. That slope only has to be used to estimate the value of permeability as well as for skin factor. So this is how the Horner's plot graph will be looking to be. At the same time, we have to, I'm going to perform this on Excel, then you will be having a good idea how to do this. Then comes pressure derivative with flow regimes. So why we are going to do pressure derivative test? This will give you a number of parameters. We are not going to discuss much number of parameters, but one of the most important parameters that can be identified by pressure derivative analysis, which will be done in well testing to recognize the kind of flow regimes. So we have three types of flow regimes. One is unsteady, steady, and pseudo steady state flow. So initially, once the well was drilled and if flow is allowed to enter into well bore, then the pressure disturbance will be generated near to perforations. So like a ripple. So when you throw a stone in a pond, how the ripples will be generated, and this ripple will start to migrate towards the end of the pond. The same way you can context here with a pressure ripple will be generated near the wellbore where the perforations have been generated over there. So once you open the perforations, a pressure ripple will be generated. That is, pressure ripple means reduction of pressure starts near the perforations once you start producing crude oil. With the pressure reduction, reservoir pressure and pressure reduction at wellbore, like PI and PW. PI will be same, but PW will be reducing. So with that pressure difference, flow will happen from high pressure to low pressure. That is from reservoir pressure to wellbore pressure. Then it will start entering into your well and it will move continuously towards surface. So this pressure disturbance, which was generated near perforations, will slowly migrate towards the end of the drainage area. So while transferring this pressure disturbance from wellbore to drainage area, the period, the transfer period, the transient period that what we are seeing over there is the condition that we name it as unsteady state flow. And the time period taken from the first ripple generated at wellbore to reach the boundary is known to be transient time period. So that means the pressure disturbance have created at perforations and it started to move towards boundary. So it will take some time. It could be 6 hours, 7 hours, or 8 hours. So until it reaches boundary, the time period is considered as transient time period. And the equation which is related to unsteady state flow is dou P by dou T is equal to F of IT. What is dou P by dou T? Change in pressure with respect to time. So dou P represents the change in pressure. You're measuring the change in pressure when time varies. So if you vary time, what is happening to that pressure? It is a function of location and time. So F of IT represents function of location and time. You can choose any location inside reservoir and change the time, like T1, T2. Like at T1, what is the pressure at that location? Then change the time from T1 to T2, then measure the pressure at the same location. It will not be the same in unsteady state flow. It will alter. So this is how we can identify that the state is unsteady state flow. When it comes to time, you can keep location constant, like I is constant, and you can change the time. So you kept a location and you measured pressure and you are changing time T1 to T2. So when your time is changing, pressure at the same location will also be changing. Keep time constant and change location. Like if you keep time at one, like after 2 hours or 3 hours, like let the time be constant for 3 hours. So after 3 hours, if you change the location inside reservoir, then pressure also will change. Near to wellbore, it could be 2000 psi. Away from wellbore, it could be more than 2000 psi, something like that. At the same time, the pressures will be having different values at different locations. So when pressure is changing, even though you keep time constant at different locations, or else when the pressure is changing at different times in the same location, that will be considered to be unsteady state flow or transient flow period. When it comes to steady state flow, this is the sequence, like unsteady, steady, and pseudo. This is how it will follow up. So when pseudo steady state ends, the life of reservoir have been completed. The production period have been completed. So production starts from the time when unsteady state flow started up. Here the production is constant. Unsteady state flow, Q will be constant. So after the end of unsteady state flow, you will be witnessing steady state flow, which is having the least time period when it is compared with other flow regimes. So steady state flow will not stay for long period. It will be having a short period. In that short period only, it will end up. What is steady state flow? Here, dou P by dou T is equal to 0. The pressure change will never be there. So pressure will always be constant at any location inside reservoir. You can change the time. You select any location. The pressure will never change. That means that pressure maintenance is happening over there. Imagine the reservoir pressure is around 2000 psi and wellbore pressure is around 1600 psi. There is 400 pressure difference is there in between wellbore to drainage boundary. So in between, there will be pressures of values which are in between 1600 and 2000. So these values will always be same when we change the time. If that is the case, dou P by dou T is equal to 0. When pressure becomes constant, derivative of constant is equivalent to 0. So that represents steady state flow. And this could happen mostly with water drive mechanism. Only water drive can able to pressurize reservoir in such a way that these pressures will not get declined. So this happens only when the water energy is supplied by aquifer. It depends on the boundary condition of aquifer also. If it is reducing, then obviously you can see the pressure also will start to get reduced inside reservoir. And that will be witnessed in pseudo steady state flow. The reduction of pressure inside reservoir is constant. Here the thing is the pressure started to get reduced after steady state flow. This is a follow-up from steady state flow. Steady state flow, pressure is constant. But when it comes to pseudo steady state flow, pressure starts to get declined in a constant way. Like at T1, The pressure is 2000 psi, means T2 it will be reducing to 1990. T3 it will be reducing to 1980, but not 1970. So every reduction, every declination, there will be a constant value will be there. So if that is the case, that is considered to be pseudo steady state flow. That means the reservoir boundary effect is influencing. So the energy from boundary itself started to get declining. It is degrading. So you have to act in such a way that we can maintain this period for longer time. If you could able to maintain pseudo steady state for longer time, then you can able to produce more amount of crude oil. Or else at a certain time period, the reservoir life will be ending. That means the production period will be ending. Beyond that, any kind of an EOR operation or anything you do, that will not have imperial effect on production. So before that particular time, we need to start introducing different enhanced oil recovery techniques to continue production in pseudo steady state flow. So these are the flow regimens, initially unsteady, then comes steady, and finally it ends with pseudo steady state flow. This pressure derivative analysis will help us to understand, so up to where the condition is prevailing as unsteady state flow. Here they have written as transient. So transient is nothing but unsteady state flow. So transient period will be ending up to here. So this is pressure buildup graph, and this is derivative graph to that. So this is a derivative graph. So if you have pressure buildup data, then we can convert the buildup data to derivative graph. And if you observe, if you plot both graphs on same graph, then definitely we can able to see the difference between unsteady state flow, pseudo steady state flow, and steady state flow. So once there will be a hump, it has generated near to early time region. So this hump represents up to here is skin zone. Then after that, the wellbore damage effect will be there. So the gap between these two graphs represents there is a skin presence inside wellbore. So near to wellbore, not inside, it is near to wellbore. So when there is a skin and wellbore damage effect, this is the hump of that particular time period. Then after that, there will be a steady continuation of flow will be there. This represents a radial flow, and this happens during transient period, that is nothing but unsteady state flow period. Then after that, if you could observe that the trend of slope is increasing, that represents pseudo steady state flow. For pseudo steady state flow, both the plots will go in positive direction. That is like this is the delta P, that is pressure buildup graph, as well as derivative graph will be looking to go both in same direction, that is towards positive side of y-axis. So if that is the case, then we can consider that reservoir have reached to, the influence of drainage boundary is affecting the production, and the flow started to move up. So energy started to decline. So pseudo steady state flow means energy is declining. So this is how we can able to identify pseudo steady state flow. If it is steady state flow, then you cannot see the increment of this graph. Rather than that, it will continue its path. But that is for pressure versus T. But when it comes to derivative, it will start moving downside. So if it is declining, then it represents steady state flow. We cannot say this if the trend is moving on the same direction, whether it is unsteady or steady by pressure buildup. But we can say that through derivative graphs. You can see the difference here. It is continuing with steady state flow for pressure buildup, but for derivative, it is decline. So these are the indications that will help us to understand whether the reservoir is witnessing either steady state flow or pseudo steady state flow. It can continue up to some time, then after that it may go up, means steady state flow period is always considered to be less compared to unsteady as well as pseudo steady. So this is how we can able to identify these flow regimes through pressure derivative and pressure buildup. So I will go to Excel after completing the presentation, and we will see whatever things that we can do in Excel. So let me continue with the topics through PPT. Then there is no need to come back again here. So directly we can go with it. So next comes frontal displacement. So what this Buckley and Leverty have given this equation for, that is fractional flow and frontal displacement. So first of all, we need to understand what is the difference between fractional flow and saturation of water. So FW and SW. Everyone knows SW is the saturation of water which was present inside reservoir pore volume. So it will start with connate water saturation, which is not zero. It could be anywhere nearby 0.25, 0.3. It depends on the kind of reservoir wetting characteristics. Whether if it is water wet, connate water saturation will be more. If it is oil wet, it will be less. I just given an ideal value, that is 0.25, which is not zero. So saturation of what? I'm sorry. Saturation of water starts at connate water saturation and it will end at residual oil saturation. So that means it is not going to end at 100%. So 0.75 represents remaining 25% of pore volume was occupied by residual oil. So remaining part is water. So water can complete the reservoir until 75%, and remaining 25%, it cannot fulfill that. It cannot just push oil and occupy that space. That means that residual oil will take its own area. So this water will not be allowed to push or bypass that particular oil. So it starts from 0.25 and it ends at 0.75. But at the same time, fractional flow water like FW can be measured at connate water saturation. The value of FW will be zero. At residual oil saturation, the fractional water will be equivalent to 100%. Means you can understand it is in between connate water saturation and residual oil saturation. You can, if you go deeply into the reservoir concepts, you can understand what is happening actually in between these two phases, connate water saturation and residual oil saturation. That means you just think beyond that what is happening. Means below connate water saturation, what is the phase of water, and above connate water saturation, what is the phase of water. That means below connate water saturation, there is no movement of water. There is that water is immobile. The water saturation below connate water saturation is immobile. It cannot be moved. It will be it is a part of reservoir rock that cannot be moved. Then after connate water saturation, that is a critical saturation. Once the saturation starts to move beyond connate water saturation, then this water will start to move so that oil will get displaced. So water actually driving oil towards the end of reservoir somehow through pore spaces to displace from the reservoir where your production well have been placed. So your injecting well is injecting water so that the saturation of water from connate water saturation inside reservoir rock is raising so that it is displacing oil from the reservoir towards your production well. So this is the job of water that is being done by injecting water. So it depends on the it is not that when you measure saturation of water inside reservoir, we will be knowing the result. Only the thing is we can know if you could able to estimate FW value, that is fractional value of water, FW, then only we will be understanding how much water is being displacing oil towards your production well. So there is a graph was given in between FW versus SW. So x-axis is SW and y-axis is FW. This is the reservoir rock where the rock is entering into one section, entering and leaving. So entering and leaving, it left some amount of flow rate that have been neglected in this equation, but we are not going into this derivation part. But for us today's class, this is important. this graph is the one which we are concentrating. So x-axis is saturation of water, y-axis is fractional flow of water. So y-axis limits started from 0 to 1. X-axis also have started from 0 to 1, but the thing is, you can observe that the graph started as at SWC. It started to move up. That means when it is moving up, fractional water started to go in positive direction. Like from 0 to 1, it started to move at SWC, but not at 0. That means the movement of water started at SWC. When you still going to inject water, SWC will start to raise up, so that the movement of water also will be raising up. So here the saturation started, it will start to raise up while the saturation of water is increasing inside reservoir. It will go up until you reach a particular point, that point we need to identify. It's a critical point. Then after that, the saturation of water will start to increase inside reservoir, but the movement will start to decrease, but it haven't ended. See, up to the point where the laser beam is there, until that the saturation of water is increasing with the movement of displacement. But after this particular point, you can see the slope is deviating towards the right side. Means what? It is the water saturation is increasing. X-axis is increasing, but y-axis is decreasing. So if that is the case, then slope will be shifting towards right-hand side path. So if that is the case, y-axis is reducing, x-axis is increasing. Means more and more injection of water is not allowing oil to get moved. So this is how the water is displacing oil from this point. So this point is considered to be a stable point, and we need to estimate the value of this particular point. Why we are going to estimate this value? There is a significance is there. I'm going to explain you for that also. There is another graph which have been interpolated on this particular graph, that is dfw by dsw. It is nothing but the same graph. The slope of each axis have been taken. It is a derivative graph for this particular S-curved graph. So derivative graph also kept on the same axis, and they have observed it started to move up until the stable point. Then after that, it started to move down. So derivative graph will help you to understand, the movement of oil started to reduce. So once it started to deviate downside, that represents the movement of oil started to reduce until the peak. The movement of oil is stable. The best value you can able to get at this saturation. So that means the peak have started to get reduced. But how to estimate this stable value? So that is important, and how it is going to affect us. Just a minute. Okay, I'm going for the next slide. This is the equation that was given by Buckley and Liberty, that x SWF is equal to 5.615. IW represents the amount of water injected by your injection well into time. It could be 10 days, 20 days. How much time have been taken to inject water? That is time period. Then comes porosity and cross-sectional area, and into DFW by DSW. So for estimating this value, we need to identify that one. I will explain you through Excel how to estimate this value. These are all parameters you can get it from reservoir data, and X represents the displacement in feet from injection well, how much amount of distance the waterfront have displaced oil towards production well. So how much movement have been happened inside the reservoir through water while displacing oil, that is X. It could be 100 feet, 200 feet, or 300 feet. How much distance is there in between production well and injection well? In between that, how much it has been displaced. So that is how we can able to identify. And where exactly is that waterfront? That waterfront is the one which is pushing oil like a wall. So we need to we cannot able to witness with any other kind of test, but only the way we can do it with this equation. That is, Buckley and Leverty have given this equation. This is the only way to identify where exactly is that interface present inside the reservoir rock in between production and injection well. So this is how, if you have all these parameters plus this value dfw by dsw, this is the one we need to estimate through graph. You can see this is the S curve, and here S curve was considered to be a straight line. There is nothing about this curve to be signified, but more than that, it can be, you can just connect a scale, straight line scale from SWC to the curve where it started to deviate towards positive side on the x-axis. So if that is the case, we need to draw a scale towards that point where it was intersected. From intersection, we need to drop scale where it will touch on your derivative axis. Here derivative graph is not there, but here it is there. So actually we need to draw a scale. I will try to show with a pen, which may not be accurate, but we can do accurately in Excel. So this is the scale we are supposed to draw on the graph. This is the scale. From where it is intersecting, we need to drop that point onto the derivative scale. And from that point, we need to project on its axis, and we can estimate the value of that. It could be 2 or 3 or any number related to this particular axis that we are going to identify. If you know this value, then you can incorporate this value in that equation to estimate this equation. This value, if it is known, then remaining all the values, if you could gather this information, then we can able to identify the interface region from injection well towards production well. So this is about the theory, and we will be doing two things in Excel. One is finding one parameter, that is permeability, through Horner's plot. Then comes identifying the type of flow regime is like pseudostat. We will see as per the data what are the kind of flow regimes that were there, that can be understood by this pressure derivative graphs. And the last one is we are going to witness this equation, and we will find out how much extent that waterfront have been displaced inside the reservoir. So let us get into the Excel sheet. I hope Excel is visible. Can anybody yeah, thank you. So first of all, I will start with the sequence how we have followed in the presentation, and the data was already kept over here. So this is dt means nothing but delta t. In Excel, I need to put symbols that will take more time. Rather than that, I'm just trying to adjust with the values that we can able to do. That is dt delta t 0.0. This is the point that we are supposed to understand. Delta t is equal to 0. So that is the one, and t power 1/4, the nothing to do with this. Tp plus delta t by delta t. See, Tp was given as 50. So already the production period have been completed for 50 days, then 50 hours. From that itself, we have incorporated that value. So this is Tp plus delta t is C11, that is this point, by delta t. So the same values will be repeated for all the values. That also was there here. You can see all the values until this many points. We have collected this value. Then delta P, this is from reservoir data. So the pressure started to increase, PWF. It is nothing but PWF. And reservoir data was observed. Flow rate, this is like surface flow rate, 146 stock tank barrel per day. And formation volume factor is 1.29 barrels per STB. And viscosity was observed to be 0.0085 centipoise. And the thickness of the reservoir was 125 feet. And our objective is to first construct pressure buildup graph. Let us see how the pressure buildup graph will be constructed. Then we can go for permeability measurement. Then after that, we will go for derivative pressure measurement. With that, we will go with flow regimes. So for construction of pressure buildup graph, we need two things. One is TP plus delta T by T delta T, which is supposed to be on, I have kept that graph, TP plus delta T by delta T and PWF. So we need two axes, and we have to understand one more thing, that x-axis is a logarithmic graph. It is a semi-log graph. So we need to estimate slope from this. So I'm not going to select the first point since it is having some error. So I will go with the second one. So this is my x-axis, which will be always on the left side. Then after that, whatever columns that we select, that will come in y-axis. So this is the graph of my pressure buildup. So it doesn't look similar to this. I will just try to compare nearby so that it will be understandable. So this is about the graph. So as I said, my x-axis should be logarithmic. So I'm going to convert x-axis in logarithmic scale. So still, this is how the logarithmic scale looks to be. This is my pressure buildup. Pressure. And why it is like this means my x is already converted to logarithmic, but here the values were in reverse. The one what I'm showing you is it started with 1, 10, 10 square, 10 cube. But actually, I haven't started here with 1, 10. It is in reverse form. Like here it is 1, 10, 100. So I will change the scale in reverse mode. So I will just go to axis tools and I will adjust the values in reverse. So you can see that it is having a similar slope like the one what we are observing here. Okay, so this is about reversing that one. And first of all, after this, we need to adjust even more. Let me expand. So I'm adjusting the values. There is this much gap is there. I want to reduce that gap. So I can give the value of x-axis to be minimum value of that will be nearby 50. No, it is not. It is crossing the 70. Could be a right value to understand this graph, and we can. I will change this type of graph to the normal points. So when you observe these points, we cannot actually identify any term over here. So, but there are two to three slopes have been we can identify from this. So how we can able to identify here, as we can see, as per the Horner's plot theory, initial points are those points corresponding to skin and wellbore effect. So we need to ignore these points which are not following the trend of this straight line. So this is the one we have to target. But in our graph, there are some initial points are there. Actually, they have been deviated from the original trend. But while seeing like this, we cannot able to identify. Rather than that, we will try to put a scale. So this is a shape which is having a straight line property. So straight line will never change. So you can use this as a scale. So you can see there are number of points which are intersecting on it. I can increase the width of this one so that it will be understood even more, and I will change the color. So in that way, we can able to identify. So you can see how this scale is being extended. It has to be on these points. Some points are deviating. Scale width is too high. Try to reduce the width. These are the points mostly which are connecting to our permeability. So these are the points. So that means we need to ignore these 3 to 4 points, and after that we can continue with this point, and we have to end nearby this point. So there are some points are there which started to deviate from here. It is an ideal way of representing, but it depends on how specifically you are doing your job over there. So I'm just giving you an ideal way of making these things. So again, so first of all, we need to match this, and I'm going to club these two as a group. Then I can move this graph. So I'm ignoring these 4 points at initial stage, and after that I'm ignoring 1, 2, 3, maybe 10 points I'm ignoring from the last. So last 10 points have been ignored from the other side, and the first 4 points have been ignored. Why? Because I need to estimate slope from this. So I'm going to estimate slope over here. So this is the graph in between. So it is the graph between these two. So I'm estimating slope for that is equal to slope. First 4 points from the starting and last 10 points from the ending. So I'm going to ignore 1, 2, 3, 4. I will start with this point since that represents. So this is my x-axis. Sorry, this is like initially we need to give y-axis. So y-axis is 1, 2, 3, 4, fifth one. From here onwards, I will go down, and I can ignore last few points, maybe somewhere around here. Then I'm ending y-axis and I'm selecting x-axis, and I'm moving to top. So until I reach the proper match. So I selected my y-axis and x-axis, and I have determined my slope. As you know, slope was be given in minus. So minus 162.6 Q naught, mu naught, B naught. That is the one we are supposed to do it. Right now, we have slope. We have the value of slope to be 0.0165. From this, I'm going to estimate permeability. And this is the formula I have. 162.6 minus Q naught, B naught, mu naught, M. That is this value into thickness. So I have reservoir data over here. So based on this, I'm going to estimate the value of permeability. So as I said for earlier, there is no minus symbol. So we are supposed to put minus symbol here. 162.6. 62.6 into Q naught. That is this into B naught 1.29 into mu, that is this value, by slope, that is this, into thickness 125. I completed the bracket and I got my value of permeability to be 126 millidarcy. So this is how we can able to estimate permeability by pressure buildup test. Okay, quickly we will go into pressure derivative. So this is the formula for pressure derivative, and this formula is pressure derivative is something that I took this formula from certain reference, but it is not that this is the only formula we are supposed to continue. There are a number of scientists have given number of formulas, but I am taking one formula which is related to Bordet. So that scientific formula, I'm using it here. So let me start estimating these values. So the slope was given over here, but I need to estimate slope that is not this slope, that is the slope between dp and dt. So I'm going to put that value here, slope for dp by dt. So change in pressure, that is minus earlier minus previous one by change in time. So from this, okay, this is about the slope, and this is my pressure derivative. Slope I minus 1, that represents the earlier slope, plus slope I, that is the current slope, average of these two by 2 into dp square. So that is the square root of this dp whole square into dp plus delta t by delta t. Then this whole term should be subdivided by production time period, that is nothing but 50. And the values, this was supposed to be constant, and from here I have to move forward. So this is my pressure derivative values for this. Some mistake was there. So I was supposed to do it here actually. So just give me a minute. But this is not dp. This is the mistake. What I have done is it is dt. So this is the mistake I have done. And one more mistake what I have done is yes. Okay, I will go with this value. Okay, from this, I will try to just go with the derivative graph, dt versus dp, which is my y-axis, and derivative graph, which is here. There are minus symbols are there. Minus. Okay, I will share another pressure derivative graph which represents the same value. So this is how the graph pressure derivative will be the same formula, same data, but the values in that Excel, I am not getting similar values to what I'm getting here. So I'm going to use this graph to identify the parameters. So let me go for dt and dp and pressure derivative. So if I include graph, so this is how my pressure derivative graphs used to be. So everyone can witness this graph. So this is how it is looking to be. By this, we cannot able to understand, and as well as the graph, what we are supposed to get is the graph like this. So this is the graph you are supposed to look at it. So the reason why it is why, because the x-axis linear, it is not coming to be like that. So I'm going to change x-axis to be logarithmic. So here, so this is how once it was converted into logarithm, you can understand the shape of this axis. And I will keep this beside at the end of the graph. That is, one is go to labels, go to height. So it has been gone to the end of the graph, and we can adjust the value of this also to be 0.001 highest, and we can make it up to 5, 7, up to 8, 2 to 3. Okay, something like this. So from this, can we identify flow regimes? This is the ideal graph. So you can see that there is a hump that representing skin and wellbore damage. Then after that, it took a radial path. There are small deviations are there, but they have their own significance that we can discuss later. Then later after that, there is an increment in the pressure buildup as well as derivative. The orange dotted lines are representing derivative pressure, and the blue lines are representing pressure buildup graph. So pressure buildup have been continued to be like this, and it started to move up. So you can see here there is a movement of points towards top side of the axis. At the same time, these points also started to move up. Of course, they were a little bit random, but it is moving in the positive direction. So that represents the end of unsteady state flow here. Then after that, it attained pseudo steady state flow, but not steady state flow. So we have two things over here. One is unsteady as well as pseudo steady state flow. I'm going to represent both over here. So unsteady, and this increment over here represents that reservoir is witnessing pseudo steady. This graph was from the same data, but there could be some issue with the formula. So that could be the only reason I'm not getting the values exactly the way how I'm getting here. So this all depends on the formula only. If you have exact formula, then we can able to get these trends. This is how we can able to construct a pressure derivative graph and how to identify flow regimes. So this is pressure derivative with flow regimes. So based on that, we can identify where exactly the path started to deviate, that represents pseudo steady, and before that, until that, it is unsteady state flow. Then let us quickly get into another graph, that is frontal displacement. So this is the graph we are supposed to generate. I have the values for viscosity of water, that is 0.5 cp. Time I have 60 days, and water injection 900 barrels, porosity 0.25, that is 25%. Area was 26,400 square feet. So based on that, let us construct a frontal displacement equation, and I need to know the value of df by dsw. Let us see how we can able to do that. So fw value I'm doing, first of all, I need to estimate the value of fw with the viscosity of oil to be 0.5 cp. So for that, the formula to get fw is equal to 1 by 1 plus kro by krw. I have the data for relative permeability of oil as well as relative permeability of water. And viscosity of water is 0.5 cp, and viscosity of oil, it is 0.5 cp. Both are having same viscosities. Let us get into that. Is equal to the formula like 1 by 1 plus kro by krw. So 1 by bracket 1 plus double bracket kro krw. Kro into mu w viscosity of water, that is this. It is a constant parameter, so I'm freezing it, not this one. Okay. After this, by krw, which is not constant, and mu o, that is 0.5 cp. I simply write 0.5 cp. So I'm going to close the brackets, and I got first one, since 0 is there, so remaining values I got it. Okay, so let me check for the df by ds value. So df by ds. So minus f df by ds, that is saturation of water, plus minus. So I got divisibles. So this is my df by ds value. So time, and I need to, other data was already available. Then I, first of all, I need to construct this S curve as well as derivative curve. Yes, 10 minutes is the time. Okay. So saturation of water, my FW and derivative graph. Insert. So this is how my derivative graph looks to be. Since it is so just I will be summarizing what I have done. This is my SW value, and I have estimated the value of FW by all these parameters This is the equation I used to do that. At the same time, the slope of the derivative graph slope I have estimated, like uh, the difference between FW values and SW values on the numerator and denominator I kept. Then I have iterated forward. So with that, I have constructed this graph. So this is the graph, and I'm going to change it into line mode so it will be easily understood. So this is how the graph of your FW as well as derivative graph, but the axis is not looking to be same. So I'm going to just change the axis to be secondary, and adjust the values from 1 to 5, 0 to 5, 0 to 10. So this is how my graph will be looking to be, and I will make it primary or secondary, and the axis is 10. Okay, so this is the real-time graph of Buckley-Leverton equation. So this is how it looks to be. So this is this FW curve, and this is DF by DSW curve. Right now, I need to estimate the value of DFW. Since both are on the same axis, first of all, I need to, you can see it is incrementing like this. Then after that, it has taken positive path. So here, this is the point where the flood front stability is available. So this is actually y-axis is FW and x-axis is SW. So FWF will be here and SWF will be here. So I'm going to insert points. This is one point. This is another. So this is my FW and that is my FWF, and this is also SWF. These two coordinates represents the best stabilized saturation for waterfront. So this is how we have defined, but more than that, I have to put a tangent over here through a scale. So I'm going to insert that also. So from this is the point where SWC is. This is the point exactly where it is touching, but of course, this is not exactly. This is the point. Not the yes. This is the point, as well as the point of intersection is this. This is SWF. And this is FW. Okay, let it go. So this is my SWC. SWC. So this is SWC where 3 points are intersecting, SWF and FWF over here. So from here, I need to draw a straight line on this graph, and from there I need to project on the secondary axis. So already there is a straight line. So I'm going to just project from the intersection of this point towards the axis. So this is exactly my DF by DSW value. So I'm going to put the value. It comes close to DF DFW by DSW is equal to, it is in between, it comes close to 1, which is coming close to 2. So I can give this value to be 1.8. So 0 to 1, it is coming. So it will be coming around 0.8, something like that. So it comes close to this point. So if you go deeply, you can estimate it, but let us give a reference value near to that. 0 to 1 is the first point, so we came close near to 0.8 something. So this is the value of dfw by dsw. So once after getting this value dfw by dsw, let us put the value over here to estimate x value. So dfw by dsw is 0.8. So x is here. So I'm going to estimate by using this formula 5.615 into IWT1 by 5A. This is the value I got dfw by dsw. Let me check. Let me see the value near to this. It is showing to be 0.8, where it is touching over here 0 to 1. So the axis 10 divisions are there. So 1.8. Okay, fine. Yes. What 5? I'm from this formula, the numerator 5.615, 5.615 into IW. IW is water injection. So here the value is there 900 barrels into T1, that is 60 days. No need to put bracket, into dfw by dsw. Since I have taken 0.8, we got that value from the graph by porosity, that is 0.25 into area, that is 26,400 feet. So let me check the value. I got the distance from injection well, the flood front have moved up to 36 feet. So this is how we can able to estimate. So from injection well, the flood front have reached to 36 feet towards production well. So this is how we got x is equal to 36 feet. This is how we can able to estimate the value of this frontal displacement. X represents frontal displacement, and this chart is frontal displacement chart, and these are the points, and I have to give x and y axis, that we can give it a little later. So this is how we can able to estimate the value of x. So I believe I have completed the portion. Hope you have enjoyed. So the process is same, only the error that I have